Thank you everyone for coming. It's my distinct pleasure to be able to introduce Arvind Satyanarayan's defense talk. Arvind's actually my last Stanford advisee, so this is a bittersweet, but emphasis on the sweet moment for me. So I've known Arvind for the last 5 or 6 years. We were lucky to convince him to come to Stanford. We were especially lucky to convince him not to leave like all the other Stanford students for a startup, and instead I think he came back from some startup experiences rejuvenated about research as his life's calling, and I think it'll really show in some of the work he's sharing with us today. It's been a very exciting set of years doing research with Arvind, and also watching him blossom into a researcher and also receive some very exciting faculty offers, which he will be able to fully accept if the committee is pleased with his work today. So I wish Arvind well in doing that.
Thank you, Jeff. And thank you all for coming. I'm really excited, including with the 11 people on the live stream, to talk about the work I've been doing for the past few years building these declarative interaction design models for data visualization. So to get started, data visualization has really gone mainstream. We as a society have come to embrace it as a medium to record, analyze, and communicate about our data. But why has it seen such explosive growth? Well, I wanted to start by just examining a couple of examples in more detail. So imagine that I had data for about 230,000 flights, and for each of these flights I knew the day and time that they took off, their source and destination cities, so the distance that they flew, and their arrival delay. Now what I could do is just dive right into this data and start visualizing it in a whole number of different ways, but it's often good to start by taking a step back and getting an overview of the data. And a common way of doing that is through the use of histograms, because they give me a sense of the distribution of the data along a variety of dimensions. And already at this high level, we're seeing some interesting trends emerge in our data set. So with this histogram down here, looking at the date, we can see this weekly repeating pattern where there are fewer flights on weekends. Up at the top there with the time of day, we see that sort of activity in airports really kicks off at about 6 a.m., but it's that evening period, 6 to 9 p.m., that's really the busiest. With arrival delay, it looks like actually most flights seem to get to their destination on time, right? Within that sort of 10-minute margin of error. And that's something you could have certainly fooled me about given my travel over the last 4 months. And finally, distance, you can see the effect of sort of hub and spoke travel in the United States, right? Most flights seem to fly between 200 and 400 miles, even though we know the United States is much larger than that. So while these static visualizations were a good first step, if I was to add some interaction techniques, the set of insights I'm able to generate is much more amplified. So this is a technique called cross-filtering. When I drag out a region of interest in one of these histograms, the bars in all of the others re-aggregate to show just that depicted region. And as I drag it back and forth, some more interesting things emerge. So here, for example, we're seeing that the longest delays occur later in the day. And this kind of makes some intuitive sense, right? Because we can imagine these delays start to accumulate and have a knock-on effect throughout the day. But the very same interaction also shows us an interesting correlation between delay and distance. You might notice as I drag that brush all the way to the end, these bars, right, for the longest flights spike. Now what that's suggesting is either airlines are very good at making up time in the air, or more cynically, we might say that for these really long flights, they're just giving themselves a much wider, longer margin of error. And so what's interesting about this is, although those static visualizations were a good first step, it was through this sort of interactive manipulation of the visualization that we were able to really start interrogating the data, asking questions, generating hypotheses, and answering them without having to construct new visualizations every single time. And besides these sort of exploratory use cases, journalists have been using interactive visualizations very effectively to communicate complex data sets to their readers. So here's an example by Amanda Cox from the New York Times, and it's from 2010. So while it's not maybe as sophisticated as some of the visualizations we see today, it remains one of my favorites because of how the story unfolds. So step by step, Amanda takes us through the various budget forecasts put out by administrations and compares them against reality. And perhaps unsurprisingly, we find that those forecasts are almost always much more optimistic than what things turn out to be. And once that narrative arc completes, the visualization opens up for much more free-form exploration. So I can go back in time and see that we achieved $300 billion of surplus in the year 2000, and we were projected to have $500 billion in surplus by 2011. We all know how that turned out. And so my research has been focused on allowing people to build visualizations of this caliber by focusing on developing new models for interactive visualization. And these new models have two main goals. The first is to lower the threshold, or the amount of technical expertise required to construct these visualizations. And the second is to enable a systematic analysis of the design space. And we'll see why this particular goal is important at enabling some new systems for analysis and design. And my research builds on the current state of the art, which is D3. You can think of D3 as a visualization kernel. It provides a number of useful utilities that we use throughout the rest of our work. And so building on D3 is first Vega, a full declarative language for interactive visualization. And by that I mean we provide primitives for not only the visual encoding, but the interaction techniques as well. And in particular, our goal at this level of what will eventually be a tool stack is to enable a very expressive design space. Using Vega, I want to be able to construct a whole different variety of interactive visualizations. Building on Vega is Vega Lite, a higher level grammar of interactive graphics. And our goals here are to enable concise specification that is particularly suited for rapid authoring as part of a data analysis process. And at the Vega Lite level is also where we start to tackle some of these questions of being able to analyze the design space.
Yeah, clarification.
Yeah.
What do you mean by full declarative? What is full?
So the question is, what does full declarative mean? And it means that we provide, that Vega provides primitives for both visual encodings and interaction techniques. The prior work that looked at declarative models for visualization only looked at visual encodings. The interaction techniques were sort of on the side. And like I said, both Vega and Vega Lite provide platforms for us to build these new systems for data analysis and design. And we've been really excited about the fact that these languages are being more broadly adopted in the community. So Wikipedia and the Python data science communities have already started to integrate them with their systems. And I've been exploring this space as well with a system called Lyra, where we've been investigating what it might be to do direct manipulation design of visualizations rather than through programming. And the underlying principle behind all of my work is declarative specification. So my models describe what the visualization should look like rather than requiring users to specify low-level procedural steps for how the visualization should be computed. And this has several advantages. First, users can focus on the design. So for a single particular design, they can iterate through it much more quickly, and they can also much more thoroughly explore the possible space of alternative designs. And I would argue that because users are no longer responsible for thinking about any sort of execution details, visualization design is now a little more broadly accessible, particularly to those with less technical abilities. It is the underlying system that implements these models that is entirely responsible for execution. So this includes things like data processing, rendering, and animation to produce the final visualization. And that also means that the system can transparently optimize any processing completely unbeknownst to the user. And we'll see some of the implications of this point later on in the talk as well. And finally is this notion of reuse and portability. So with just a single declarative specification, I can dynamically bind it to different input data at runtime, and I can also retarget it to different devices and modalities, so desktop and touch and so forth, with very minor, if at all, any modifications to the specification. And these advantages of declarative specification have been well studied in other domains. So we can think of, say, SQL in databases provides a very consistent declarative syntax, regardless of the database engine that you're using. And it's also led to a ton of research into query planning and optimization and so forth. And similarly with HTML and CSS, we've got a consistent declarative syntax regardless of the browser or the device that we're viewing a web page on. And in visualization, declarative specification of visual encodings, going back to James's question, has been well studied. Yeah, Manish.
So those are the advantages?
Yes.
What are the disadvantages?
Of declarative specification? Yeah, so Among them, the question for the live streamers is, what are the disadvantages of declarative specification? One of them is, I would say the biggest one is probably the fact that if you're trying to debug what is happening behind the scenes, because the system is entirely responsible for execution, you need to really understand that much more lower level execution model. But I sort of see that as an opportunity for us to start developing new platforms for debugging and sort of understanding the execution model that are much more aware of the semantics of these languages rather than requiring users to go in and put in a breakpoint somewhere in the Vega or Vega-like code.
I would have expected you to also say that expressiveness is lower than
Then a full, yeah, so that's, yeah. So the expressiveness of Vega and Vega Lite is certainly lower than just, say, free-form programming with D3 and JavaScript. Yeah. But there are certainly ways where, by architecting the languages to be fairly extensible, that we're able to, tackle that and not have that sort of gap be as salient. Chris?
I have a very dumb question that we should probably take offline. But I don't know, what can you give me examples of like the visualization bugs that
Yeah,
are difficult?
particularly, so the question is, what are visualization bugs? The simplest one would be, you map your data to some sort of visual variable, the x position, the y position, or whatever, and it just doesn't look right. The bars in your histogram may be overlapping, your axis may not be aligned correctly, things like that. And you're not sure why, how do you even start to really debug that? On the interaction side, it's much more complicated. So, if I drag my mouse around here, why has my visualization suddenly gotten into this particular state? And how do I trace that and trace, basically the propagation of data through this network? But I'm glad you asked those sets of questions because I will answer them through formal slideware very soon. So declarative visual encodings have been very well studied. So of course, we start with our raw input data. And a common data set here is the iris data set. I'm seeing a couple of nodding heads, so I think some of us are familiar with this. This is just a multivariate data set where we're measuring the lengths and widths of the petals and the sepals of 3 different species of the iris flower. Now, the core operation in visualization is to take this raw input data and map them to visual properties, things like position, color, and size. Now, to simplify that mapping, most visualization models offer these scale functions. So say I wanted to construct a scatter plot. I would need an x scale to take, say, the petal width and map them to x coordinates. I would need a y scale to take the sepal lengths and map them to y coordinates. And maybe I want to color my points based on the flower species, and so I'd need a color scale for that as well. Guides like axes and legends help us visualize the scales, and then marks are really what we think of in terms of visualization. There are data representative graphics. Their properties get determined by data values, and in the case of a scatter plot, we probably want to choose a symbol mark. Now, we've got a scatter plot here. It gives us the correlation between 2 of the dimensions in our data set. But as I said, iris is a multivariate data set, so wouldn't it be nice if we could see all those correlations in concert at the same time? So to go from that single scatter plot to now this matrix of scatter plots, I need a little bit more input data. So which fields am I interested in correlating? And then I need to transform them to calculate a cross product and get the full dimensions of my scatter plot matrix. Now, most visualization languages also have a full plethora of these transformations, things like filtering, sorting, grouping, layout algorithms, and so forth. And so we've constructed this static scatterplot matrix purely declaratively. But what now would happen if we were to introduce a common interaction technique called brushing and linking? So here, when I drag out a region of interest in one cell of the scatterplot matrix, the points that correspond highlight across all the other cells in the matrix as well. Now, this is the canonical D3 example, and as I mentioned, we've got declarative specification for the visual encoding, but the interaction is actually specified imperatively with 3 event handling callbacks. These callbacks fire when we start dragging out that region, when we're done dragging, and if we ever move that region around. So what are the problems with specifying interaction in this way? Let's just zoom into the code a little bit and examine it more closely. So the first is that this is a very inconsistent notation style. It sharply breaks with all of those advantages of declarative specification I mentioned earlier. Here in particular, we're exposing a lot of lower level JavaScript execution details, like what is the function context of this brush star function, which is what populates this variable and things like that, right? Very low level things that don't have anything really to do with the particular interaction technique I'm specifying. Second, it falls entirely to the user to manage any sort of interactive state. And this can be very error prone and complex, getting back to your question, Chris. So here, for example, every time we start dragging, we have to clear out any of our previous state and reset it. And if you forget to clear it out or reset it, you start to get really funky, interesting interactions that are not what you want. And finally is this notion of side effects. These imperative callbacks have been registered outside the rest of my specification. So any changes that they introduce, any modifications that they make to the visual appearance also happen externally. What this means is if we get a bug in our visualization, there are now multiple code paths that we need to trace down to understand why the visualization looks a particular way. Now, I call these three things usability issues with imperative callbacks, but there are a more fundamental set of issues with the representation of imperative callbacks themselves. So the first is, how do we analyze the interaction semantics? And by this I mean, what is the user trying to do when they do an interaction? What is the data query that they're trying to execute? And perhaps even what questions are they trying to answer ultimately with that interaction? It's very hard to know how to analyze this code block to answer those types of questions. We could maybe do some sort of static analysis, but that would tell us a lot more about the particular JavaScript syntax we've used rather than some of these higher level semantic questions. Second, it's also very unclear what the space of alternative designs is. How would I make a particular modification here to change the way that brush region interacts with my visualization? I don't know, it's very unclear. And finally, because of both of these issues, it's very hard to do any sort of higher level inference, things like automated design and recommendation with imperative callbacks. And so to address some of these issues, I decided to do a PhD. And so I'd like to walk through these projects starting right at the bottom with Vega. And as I mentioned, because we're at the lowest level of our Vega tool stack here, we're really focused on this question of how to enable expressive design. And the way we've sought to address it is with a couple of key insights. The first is that we could model user input, so things like mouse button presses and moves and so on and so forth, as a form of streaming data. And if we were to do so, we'd be able to adapt and extend techniques from the functional programming languages literature as well as streaming databases. Now, I'll unpack these concepts over the next few slides, but the high order bit is that when an event occurs, Vega automatically recomputes any interactive state and propagates that to dependencies. Those dependencies in turn are automatically reevaluated, and the visualization is automatically re-rendered, and the user is not responsible for any part of that execution pipeline. So here are those visual encoding primitives from earlier, and we add to them these event streams. So imagine that we had a bar chart and we just moved our mouse pointer across those bars. What we'd observe is a stream of mouse move events that occur on rectangle marks. Now in Vega, we've simplified the ability to construct these event streams with a simple event selector syntax modeled off CSS. So the simplest event stream is just the event type, and we could also prepend it with the source of our event. So in this case, rectangle and mouse move. Now the benefit of these event streams is they really simplify our ability to sequence and compose these raw input events. So what if I wanted a stream of drag events? Right? One way of modeling drags is just to say that they are mouse moves that occur between a mouse down and a mouse up. Now what's fun about this event selector syntax is that this is a fairly complex operation that you would have to do with imperative callbacks. It would take at least 3 imperative callbacks and some amount of external state. And with event streams and the selector syntax, we really boiled it down to a single string. And this single string in and of itself is fairly expressive. We can do things like filtering and time intervals and debouncing and so on and so forth. Now, event streams themselves are a first-class data source, so we can take them and wire them directly up to marks to visualize whatever interaction technique a user is performing. But for added expressivity, they can also be composed into these dynamic variables called signals. So for example, we might have a signal called min coordinate that just extracts the x and y coordinates every time the mouse button is pressed. So every time the mouse down event fires, the min coordinate signal updates with those x and y coordinates. And by default, because the signals are just being derived from these event streams, their values are in visual or pixel space. But to be able to reuse an interaction technique across different visualizations, we want to lift that to the data domain. And so for that, we have these scale inversions. So we can take our min coordinate signal from earlier, invert it through our x scale, and now we get a min datum signal out instead. So now our interaction technique is being defined in data space. The next step is to really start to build out our interactive queries. And those are through these predicate functions. And they're just simple Boolean functions that return true or false. So you can imagine if we had a min and max datum signal, a predicate function might give us the ability to sort of select points that fall within that range. And then the final step is to use predicates to drive some visual change to our visualization. That happens with these simple if-then-else rules called production rules. So we could say, for example, the points that fall within that region, color them in gold. And for all the other points, leave them gray. And that's the basic setup that we need to get our brushing and linking example from earlier, but now constructed entirely just through the composition of these declarative building blocks, rather than writing any sort of imperative event handling code at all. And as I mentioned, we're really focused on building an expressive design space. And so here are just some of the interactive visualizations we've been able to create entirely declaratively. And I wanted to call your attention to just a couple. So here, for example, is the cross-filtering example that we started with, and then the budget forecast up at the top. And both of these are visualization, or this one is a visualization constructed by one of the members of our community. It's an NBA shot chart, and you can see as you sort of interact with all these various components, all the others stay in sync as well. So the number of shots attempted, point score, all those things continuously update. And here is a recreation of a research project called DIMPViz. And what it's trying to do is emulate Hans Rosling's style narrative visualizations. So this is time series data showing the fertility of various countries against the life expectancy. And what we can do is grab a hold of one of these points, and it shows that point's trajectory through time. As I drag it back and forth, all the other points move in concert as well. And so this was a technique that a couple of folks, Brittany Kondo and Chris Collins at the University of Ontario, developed the first time with a sort of very custom-built library, and we were able to recreate it using Vega. So what are the advantages of Vega's approach? Of course, a high expressive ceiling, but also users are now no longer responsible for any sort of execution concerns, things like managing and propagating state. As a result, they can really focus on those interaction design decisions. What events should trigger the interaction technique? How should those affect some change to my visualization? So on and so forth. Signals are also a particularly interesting component because they serve as an abstraction barrier. So here is our min coordinate signal from earlier. And what we can do is just go ahead and replace the event streams that trigger it without touching any of the rest of the downstream application logic. And so they provide this really interesting abstraction barrier that simplifies our ability to retarget interaction techniques across desktop and mobile and so on and so forth. And so that DIMPViz example that I was just showing you, works exactly the same on both desktop and mobile just by adding additional touch events to the event stream. And finally, because Vega is responsible for execution, it's able to perform a number of optimizations to the processing that's happening. So what's happening behind the scenes is that declarative specification is being computed and a data flow graph is being generated. And without getting too bogged down in the details, what this gives us is basically interactive performance that is at least twice as fast, if not more, than the current state-of-the-art D3. And here are just a couple of the benchmarks that we had run a couple of years ago. And what you can see is that in all cases, the green Vega line is above the purple D3 line. And what's particularly interesting is this dotted line here, which is the threshold of interactive updates. So once we fall below that line, users start to notice lags and jitters in the interaction. And what you can see is, in almost all cases, Vega far exceeds D3. In the most dramatic case, down here with the time series overview in detail, D3 falls below that interactive threshold at about 3,000 points, and Vega is still going strong well beyond that.
So is that like an expert D3 programmer, you or something? Or
Yeah,
is it
so
the
these,
average?
so the reason we chose, so the question is, who's writing this D3 that we're comparing it to? The reason we chose these three is because Mike Bostock has canonical examples of these three interaction techniques. So we're comparing, the canonical D3 examples to our canonical Vega examples, and this is the effect we see.
What's the intuition? I mean, I totally understand all the stuff about why it's easier, better
Yeah.
for programming
Yeah.
and stuff. What's the intuition of why it's more efficient?
Yes.
When
So-
I think about other systems like this, like constraints and garnet and
Yes.
all these things, like they made it slow. And
Yes.
So I'm trying to understand why.
Yeah, so why are these so much faster? So the biggest, there are two big reasons. The first is that because we're sort of decoupling specification from execution, what that means is we can target different renderers with the same specification. D3 is tied to the DOM, and the DOM is slow. With Vega, we can actually target canvas rendering, WebGL rendering, whatever it may be. Here, I'm just showing you Vega using the SVG renderer versus D3 using the using SVG, so that we're comparing apples to apples. So the effect that we're seeing here is because everything underneath the hood in Vega is streaming data. So what that means is we're able to do sort of very targeted recomputations as well as very targeted re-renders. Versus with D3, everything is batch computed. So if you make a change to your data or you do a particular interaction technique that recolors those points, it has to do, recalculate all of that from scratch. But Vega can just make those sort of very targeted computations. There's actually, with the data flow graph, a bunch of other sort of optimizations we're doing behind the scenes, sort of inlining a bunch of computation where appropriate and things
So
like that.
did you get that kind of speed up from the start, or was it after you had it for a while that you started to see all the kind of optimizations that you could add because you had that?
Yeah, so that's a good question. So just building out the sort of streaming architecture, we saw a huge improvement. And then, we started to investigate how could we push that further with these sort of optimizations. So it's a little bit of both. What's interesting is actually we're working on a new so this is the benchmarks for Vega 2. We're actually about to release Vega 3, which, has a number of commonalities in terms of sort of the concepts and the underlying principles behind the architecture. But the optimizations that we're doing are very different. So, we want to see what sort of wins that we get there and things like that. So these are the advantages of Vega, but what are some of the drawbacks? Well, I would say that Vega is still too low level, and by that I mean it still requires a fair amount of expertise to craft these visualizations. You need to understand all of these sort of reactive primitives and how to wire them up and so on and so forth. And because we're focusing on an expressive design space, there's a near infinite way of combining all of these things. And so it's still fairly difficult to analyze a design space and come up with those sort of alternative designs. And so we move from Vega up now to Vega Lite, where our goal here is to answer the question, what are higher level abstractions for interaction? And in particular, the way we've chosen to sort of answer that question is by trading some of that expressivity for gains in concision. So why is concision important? Well, if there's less to write about, then users have less to think about. And if they've got less to think about, then there's a commensurately lower threshold that they need to cross to begin to write these Vega Lite specifications. And in particular, by having a concise language, we can enable a much more rapid authoring process. So imagine users like data scientists. Visualization is just one part of a much broader, longer process for them. They don't really want to get down in the weeds and start crafting a very custom visualization, but they would just want to produce something that they recognize, analyze it, and move on. And so a rapid authoring process is really important for those kinds of users. And finally, with a smaller language vocabulary, it becomes much simpler for us to sort of systematically enumerate possible designs and sort of generate them without completely sort of automatically. Let me plug my laptop in so it won't die. There we go. So how do we actually start to think about a concise specification language? Well, what we've done is encapsulate recurring design patterns that we observe at the Vega level, and we've encapsulated them in reusable and composable abstractions in Vega Lite. And by going up the ladder of abstraction, we have to necessarily sort of introduce some ambiguity in the language. And the way we resolve those is by sensible defaults that can be manually overridden by the user. So let's make this a little more concrete. Here are Vega's visual encoding primitives. And in Vega Lite, we take scales, guides, and marks, and we put them in these things called encoding channels. So here is the simplest Vega Lite specification. You can see it's just a JSON object, and we've really boiled down the specification to its most declarative form. We're just talking about input data, a particular mark, and then mappings between data fields and visual properties. So horsepower on the x-axis, miles per gallon along the y, and the origin is the color of these points. And this Vega Lite specification actually compiles to this full-blown Vega specification underneath the hood. And actually, I was only able to fit this specification on screen because I condensed large amounts of it behind these ellipses. But even then, you can see we're talking about sort of an order of magnitude more concise on the Vega Lite side. So how do we get there? Well, the reason is we're omitting a lot of low-level details, things like the scale types and the axis and legend definitions and so on and so forth. And those are being filled in by the Vega Lite compiler. Now, of course, as a user, I might know better, so I can go ahead and override those defaults in place. So here, for example, I'm saying use an alternate color palette, not claiming that this is any better than the one we used before, but that's how I would go ahead and just say, use these colors instead of those default ones. Now, there's a lot more to talk about how Vega Lite does visual encoding, but for the purposes of my defense, I wanted to focus on how we enable interaction techniques. So Vega Lite takes event stream signals, scale inversions, and predicates, and it encapsulates them in this new abstraction called a selection. So let's look again at some examples. The simplest definition of a selection is a name, in this case picked, as well as a type, here single. And we've kept around those if-then-else statements to easily parameterize the rest of the specification. So we can say if a particular point is selected, color it in its origin color. If not, leave it in gray. And this is the sort of interaction technique that we're seeing, and the way it's being driven is through those selection types, which provide a number of default values. In this particular case, the default values are saying, on click, select just that particular point that was being clicked. So there's that one-to-one mapping. And of course, besides a single point, we'd also be able to select multiple discrete points just by changing that selection type from single to multi. And now the first point gets selected on click, and additional points get selected on shift click. Now, just with visual encoding, we can override those defaults in place. So rather than saying, select on click, maybe we want to select on mouse over, and now we get this sort of very interesting paintbrushing effect that might be useful if you want to highlight, a region of interest as you're sort of communicating about your data. But if we always had to go ahead and override these defaults, well, then we've not really abstracted anything at all. Right? And the user still needs to dig into what ultimately becomes Vega. So besides selections, Vega Lite also has these selection transformations that manipulate the definition of a selection in some set ways. So here we see, once again, horsepower against miles per gallon. And a question as an analyst might have is, how did the number of cylinders these cars have play into this trend? So what I can do to answer that question is invoke something called a project transform to rewrite, selections pro. Keynote quit unexpectedly. Hey, Jeff. I think my computer's trying to do a lot between a Google Hangout and a live stream. Where do we stop? Here? Yeah. All right. Hopefully it continues. So yeah, what if we wanted to know how the number of cylinders plays into this trend? We can invoke this project transform to rewrite the selection's predicate function, and so that now when I click a particular point, all other points that have the same number of cylinders get selected as well. And so we can see, right at the top there, we've got our 3-cylinder cars, 6 cylinders in the middle, and 8 cylinders right at the bottom. But just by sort of clicking randomly, I don't get a sense of how exhaustively am I searching through my data set. Other cars with 3 or 5 cylinders in the data set, I don't really know just based on this sort of random clicking. And so, yeah.
Can you explain this a little more? I don't really get it. So I have this fields.
Yeah, so underneath the scenes, underneath the hood, if you remember, these selections are encapsulating a bunch of different things at the Vega level.
Right.
One of those is a predicate function, right, to identify which points are in my selection or not. Now, the default without this green bit is to say that predicate function is just identifying points one-to-one.
Yeah.
So a point I click on is in that selection, that's about it. What the project transform is doing is changing that predicate function to say, well, all points that have the same field, in this case the cylinders field,
So you had
are
to
also.
know that in that data set there was a cylinders.
The user had to know, yes. So
Right.
the user is writing this.
Right.
Presumably the user knows
So
their
that-
data
that
set.
In that data set there's
Yeah.
also a cylinders field.
Right. Now
And
there.
now it's saying anything that matches across that.
That's right.
And what does it mean that you have both the type single and the cylinder field? Like, what does it mean when those are together?
Right, so what it's saying is basically I can select a single cylinder value, right? So that's why I can only do, say, 3 cylinders at once, or 5 cylinders, or 8 cylinders. If you were to change it to type multi, then I could click and shift click to select different groups of cylinders. I could select 3 and 5 cylinders, or 3 and 8 cylinders, and so on and so forth. Yeah, Michael.
What is semantics embedded in like lines starting with a dash?
Oh yeah, so this is, to simplify the specification, this is just YAML. So the dash implies it's an array, so that's it. Yeah, I didn't want to get bogged down in sort of the JSON of it all. So YAML is kind of neater in that way. Any other questions?
Is there a reason for JSON? I mean, I always thought it was because it was good for machines.
That's exactly right. That's the main reason, because it's good for machines.
But you don't want, but I have to write in this stuff now.
Yeah,
Unless
so.
I use your next tool up.
Right, so there are a variety of ways to address that, right? One is using things like YAML, which are much more human-friendly. So the reason we chose JSON is because it's sort of now essentially become the de facto standard for a lot of this sort of interchange, and it's trivial to build wrappers on top of it to make it easier for humans to write and things like that. And really, by the end of my talk, what I would propose is that maybe we shouldn't even be writing these things at all, right? It's kind of bizarre that we're writing textual things for these things that are inherently interactive and visual. Yeah. So in the interest of time, I'm going to power through. Like I said, we're just sort of through these direct clicks right now, not getting a sense of how exhaustively are we searching through our data set. So another way we might drive these interaction techniques is through the use of query widgets. And we can invoke those with this thing called a bind transform. So when I add that to my specification, I now get this range slider. My direct manipulation interaction is still preserved, but I can drag this range slider back and forth, and I can see, oh, wait a minute, actually I do have some 3 and 5 cylinder cars in that data set. But there's only like 3, or a handful of them, and so my ability to have actually picked those out by clicking is pretty unlikely. And because the specification language is so concise, as an analyst, I can just go ahead and interactively, generate and evaluate hypotheses without having to really, massively change my specification. So now with just a couple of lines of additional code, I'm looking at not only how does cylinders play in this, but how does the year that the car was manufactured play into this trend. And so we're, as we drag that year's range slider back and forth, we're thankfully seeing those points move up the visualization. So we're seeing the cars getting much more efficient. Phew. So what is particularly important about these selection transformations is that they're part of a grammar of interaction. And by that I mean that they're reusable and composable across these selection types. So we've seen it with type single. Of course it would work with type multi, but we've also got a type interval to allow us to select a continuous region of points. And so by default that region is both in the x and y, but we could use the project transform to restrict it to just a single dimension, so in this case the x dimension. And we can also use the bind transformation to bind that interval to the scale functions of my particular visualization. Any ideas what's going to happen once I do that? I can start to pan and zoom my visualization instead. And so what's happening now is, oh, I thought I had a slide there. I've given so many varieties of this talk that I don't remember anymore. So what happens is that these interactions manipulate the selection, and the selection is now bound to my scale functions. And so all that data is flowing through the visualization, but is encapsulated just through these three transformations. Yeah,
Can you
John.
do disjunctions? Can you build disjunctions here?
Yeah, so the way you'd build disjunctions are basically through two separate selections and combine them either in these, basically in their application. So either in these production rules or in filters or what have you. Yeah. So all of these interaction techniques I've shown you in Vega Lite have been constricted to just these single views. But as we saw in those earlier examples, interaction techniques are much more effective when they're working across different visualizations. And so while there's not an analogy to Vega, Vega Lite also has these view composition operators. So this includes things like layer, to take one view and put it on top of another, concatenation, both horizontally and vertically, to put views side by side, repeat, that is just sort of a data-driven way of doing concatenation. And so the full data set is repeated in each of these subviews, but we're just varying the particular axis that is being plotted. And finally, facet, that takes our data set and subsets it out, generating one view per each of these facets. And what's particularly important about these operators is that they form an algebra. So the output of some of these operators can also serve as input to them as well. And so you can start to build these very complex layered and multi-view displays like you see at the top of this tree. And you can build these very interactive dashboards. So let's see that in the context of an example. Here is just our specification from earlier with that single interval selection. And if we introduce just a single repeat operator, we've now got brushing and linking in our scatterplot matrix. And really, we're just talking about tens of lines of code. And if we just add another interval selection and we bind it to the scale transforms, we can not only brush and link in that scatterplot matrix, but we can also pan and zoom the cells with all of those cells staying synchronized across all those views. Now, while Vega Lite is not as expressive as Vega, getting back to Manisha's point earlier, we can still generate a number of common and custom techniques. So here is something called an overview plus detail. When I drag out a region of interest in that top area chart, I see those points at a higher resolution in the bottom, and that's just an interval selection bound to the scale functions. Similarly, using a single selection, I can interactively renormalize this stock price time series data. And finally, sort of our behemoth of an example here is a variant of the one I started this talk off with, but rather than having just the blue bars dance around, this cross filter fills them up in gold instead. And so what are the advantages of Vega Lite? Well, there's a much lower threshold for understanding and constructing these interactive visualizations. Users don't have to understand reactive semantics at all. And as you saw, we can construct both custom or common and custom techniques. But what's particularly unique about Vega Lite is for the first time we can start to analyze what the semantics of the interaction a user is performing in the visualization are. So by that I mean, how many points are being selected? Is it just one? Is it many? Is a whole region of them? How are they being selected? Is it on click, on hover? Are they using a Voronoi tessellation to accelerate some of that selection? Is it with query widgets? And perhaps most importantly, what is the data query that is being interactively specified, and how can we start to analyze that in higher level applications? And finally, this ability to sort of rapidly explore the design space. I've already sort of hinted at this with the examples I've been demonstrating so far, but with basic atomic changes, just single additions to my specifications, I'm able to generate dramatically different visualizations. And these are just one set of examples. There's a whole sort of graph of these that we can now, for the very first time, really start to systematically enumerate. So what's interesting about this graph is, just like before, each of these edges represents an atomic change to my specification. I've just changed one thing in the specification. And we've gone from just a static scatter plot up there to a scatter plot matrix down to that paintbrushing effect by just using a Voronoi tessellation and so on and so forth. And this is just a very tiny portion of this entire design space. And this notion of being able to systematically enumerate the design space has already been useful in these higher level systems for analysis and design. So my colleagues at the University of Washington Interactive Data Lab have been building a system called Voyager to recommend visualizations to data analysts. So what's happening behind the scenes is analysts indicate fields of interest, and Voyager is enumerating that entire design space, pruning and clustering and ranking those designs to suggest the most appropriate visualizations for a particular subsection of the data set. And in studies, we found that this enables people to much more broadly explore their data set rather than fixating on particular visual designs and deep diving down particular hypotheses. And as I mentioned at the start of my talk, we've also been really excited about the uptake that we've been seeing with both Vega and Vega Lite. So we've been honored to work with folks at Wikimedia, as well as with the Jupyter and Python data science community, to really build Vega and Vega Lite into their systems. So on the Wikipedia side, for example, there are 800 pages on English Wikipedia that use Vega visualizations. Here is one example. So this is the page of the most expensive paintings ever sold at auctions. And there's a long data table here that you could peruse. But here's an interactive visualization of it. We can hover over those points to see the thumbnails of those paintings. We can use the legends on the right-hand side to filter those out by artists or time period and things like that. And we can see, are there some interesting trends that emerge.
This is Vega Lite or Vega?
So this right now is using Vega. We're about to release Vega Lite with all of this interaction stuff that I talked about, and they're super excited to get it up on there. Because
Wikipedians are the ones
yeah.
who are doing the authoring.
Yes, that's our eventual goal. This was actually authored by us, but really as a demonstration of how powerful this approach can be. And actually, on their mailing list, when Vega was first announced as being on Wikipedia, they were just sort of really over the moon about it. I think some of those points I made earlier about how difficult authoring these things has been hurting us there, which is why we're excited to see what happens once Vega Lite is up there.
Is this the only interactive stuff in Wikipedia, or is there other stuff?
There are. So 800 is both static and interactive. I don't know off the top of my head what percentage of those are interactive, but there's
No, I mean, they're using your stuff. Are there other technologies that they're using to do interactive visualization?
Oh, yes. So for maps, they're using, I want to say Leaflet or one of these things to do interactive mapping. Beyond that, I'm not sure.
And the reason there's millions in other languages is
Yeah.
what?
So why there are millions in other languages? Turns out, I think it was the Vietnamese or Hungarian Wikipedia top-level editors were really taken by these visualizations. And so what they did is on each of the talk pages associated with an article, they added a Vega visualization to basically track page views. And they just enable that at the top level. So every page on Vietnamese or Hungarian Wikipedia now has those. So that worked out for us. And on the Python data science side, we've heard that there's interest from a number of other Python vendors, so folks like Matplotlib, Bokeh, and Plotly, about possibly adopting Vega Lite as a standard for visualization specification in those tools as well. So you can think of this just as different browsers all targeting the same HTML and CSS, but doing vendor-specific things on top. And particularly at the Vega Lite level, we've been really excited about the ways in which our users have been reacting. So in a recent review, Dan Saber said it is sort of this type of one-to-one-to-one mapping between the code that he writes, his thinking, and the ultimate visualization that is his favorite thing about Altair, which is the library that wraps Vega Lite. And the Altair team themselves have said that they consider Vega and Vega Lite to be our best existing candidates for principled, lingua franca of data visualization. So, very encouraging feedback from the broader community. And besides this ecosystem, I've been studying this space as well with a system called Lyra. And it was motivated by this realization that there's so far been a fundamental mismatch between these textual specifications to express visual and interactive output. And so I'd like to demonstrate Lyra to you by reconstructing this classic chart, again from the New York Times, this time by Hannah Fairfield. And if you thought this was a line chart, I would forgive you. It's not. It's something called a connected scatter plot. So we've got along the x-axis the miles driven per capita each year, and along the y-axis the price of gas. Each of the points in this scatter plot is a year in time, and it's the path that connects the plots that gives us our time series. And so here is the Lyra interface, and we reuse a lot of metaphors from graphic design packages. So we've got front and center the canvas, and a lot of the interaction techniques will happen there. Up along the top, we've got a toolbar of our mark types and functionality like undo, redo. And along the left-hand side, we've got our visual inspectors, our way of importing data and so forth. So if we go ahead and import some data, we can do it from a URL or just copy and paste it in. We get a little preview of our data with that data table. Now we can go ahead to that toolbar at the top and add a line. And the basic operation to do our data mapping is to drag a data field off the data table. And once I do that, you see the canvas lights up with these cyan regions. These cyan regions are called drop zones. And when I get near one of them, it gets selected, a technique called a bubble cursor. And when I drop it, Lyra begins to intuit and infer the appropriate scales and axes and legends that I need to construct my visualization. And so with just a few drag and drop operations, we can not only add symbols and color them in and so on and so forth, and we're able to sort of very rapidly get close to Hannah Fairfield's original design, but now without any programming whatsoever. And what's interesting about the way Lyra is working is that the direct manipulation operations are actually producing statements in Vega Lite, and those are being merged against a full-blown Vega specification that is basically Lyra's backing data model. What that essentially means is users are able to fluidly move between Vega and Vega Lite without ever realizing that they're making any sort of explicit design decisions in terms of what tools to use. And we think that that is why we've seen some really positive feedback in both lab studies. So folks saying, Lyra makes me feel much more in control of my visualization, and that there's a real joy in using Lyra, but also in the real world. So in a recent review, Lisa Rost, an Open News fellow at NPR, said that Lyra is what Illustrator should be for data visualization. And so this is a newer version of Lyra that we've been working on in the lab, but an earlier beta version that we released a couple of years ago has been in use by about 1,500 users a month, including journalists who want to rapidly prototype a particular visualization before getting into the D3, and educators who find that Lyra is a great way of teaching what interactive visualization is without bogging students down in the D3 or the JavaScript and so on and so forth.
Is the idea that you would ever look at the underlying code for that, or just no, you would look in the tool? And also,
It's an open question.
How much Vega-like code would be that visualization right now?
So the Hannah Fairfield's design, I think we've actually produced most of it in Vega Lite. I think there's an example online that's almost all of it is Vega Lite. There's in the actual original one, there's a bunch of sort of custom labeling that happens that you could probably do in Vega Lite. You just have to position it by hand and things like that, which is really where the sort of interactive direct manipulation ability is most powerful.
So how much code is it?
In Vega Lite,
Yeah.
it would be on the order of tens of lines. So I don't know, so yeah, 30, 40, I don't know. Somewhere
So
in that
it's
order.
not even so big that you could inspect it
No.
and modify it.
That's right. So you could, if you wanted, write it by hand within a half hour, not even 15 minutes. Yeah. So to review, I've been working through or talking through a number of these different tools to really enable interactive visualization specifications. So we've got Vega, which gives us a full declarative language with primitives for visual encoding and interaction, really enabled a very expressive design space. We've got Vega Lite that gives a much more concise specification language, really facilitated a very rapid authoring process and gave us the ability to systematically enumerate that design space. And both of those enable these systems for analysis and design, one of which is Lyra, where we had the ability to sort of do drag and drop interactions rather than doing textual specifications. And what's particularly exciting to me about this work is that each of these points in the tool stack, we believe, provides a platform for further research. So looking ahead, what is there left to do? Well, at the Vega level, we can really start to think about, well, how do these techniques scale up to visualizations of massive data sets? And some of my colleagues at the Interactive Data Lab have already started to think about, well, how might we partition that data flow graph that Vega is constructing between a client and the server? And can it automatically adapt based on some of these interactions that a user is doing? So maybe at the start, some operations are occurring on the client, but as the visualization is in use, some of those operations might get shifted to the server or vice versa. And now that we've got these higher level semantics of our interaction technique, can we begin to predict the future interactions a user might perform and prefetch those results from our backend database? At the Vega Lite level, we might start to empirically derive principles for interaction design. And this sort of analogies to how we understand what makes effective visual encoding. We've done a bunch of sort of graphical perception studies. Can we extend that to interaction techniques? So can we enumerate the Vega Lite design space, and with each of those generated designs, can we classify them based on some analytic task that they answer? And finally, can we put all of those alternatives in front of users to understand what are those sort of contextual things that a user sort of really responds and resonates with. And finally, at this Lyra level, what about automated design and inference? So an easy win here is something like a visualization linter. Can we identify poor design choices both on the static and the interactive side and recommend improvements? Can we think about even higher levels of abstraction, things like interaction design by intention? So everything I've described so far I would term as sort of the operational semantics, right? So I have to say, when I do this particular interaction, make this particular change on my visualization. What if instead the user said, here is just the ultimate question I had, generate for me the most appropriate interaction technique to answer that question? And to get at that, we've also been looking at, how might we do interaction design by demonstration in Lyra? So could we hit a record button, and on the first click, Lyra suggests, a single selection. And on additional clicks, it might suggest either a multi-selection or selection transformations that I could apply. And then I could just treat those as data fields and drag and drop them onto my visualization. But looking even more broadly, one of the things I've been very excited about with visualization is I believe that it serves as a great petri dish for studying these broader HCI-related questions. And I think a lot of our insights have the potential of generalizing across other domains, particularly web design, computational journalism, and machine learning. I mean, in particular, can we start to build toolkits that are aware of these domain-specific representations? Because if we could start to build in some standardized inference algorithms, like of the nature that Lyra might eventually have. And at the very least, we could start to do some automatic instrumentation of functionality, things like undo, redo, and so on and so forth. The ultimate goal is to really elevate interaction as a first-class artifact of system design. By that I mean make interaction a property of that representation. So a good example I like to use here is, if on your laptop you have something like OmniGraffle or Visio, these very powerful diagramming applications, you've got a very powerful interaction technique to lay things out on your canvas. You can snap them to grids, you can snap them relative to each other, and you get all these guides and so on and so forth. And we also know in the HCI literature that people use the spatial arrangements of icons on their desktop in meaningful ways, right? They cluster icons together, pile them, and so on and so forth. And yet on the desktop, that's entirely freehand interaction. Why can't I rip out my sort of layout algorithm from OmniGraffle and apply it to my desktop icons instead? Those representations aren't exactly the same, but they're very similar. The interaction technique should get me 85, 90% of the way there. So I think there's potential for the ability to sort of generalize these insights, not just in visualization, but HCI more broadly. And so just before I wrap up, since this is a defense, there's a lot of sort of folks I need to thank. I've been particularly lucky throughout my career to have had fantastic mentors. First and foremost, of course, is my advisor, Jeff Hare. Jeff has really been in every way the consummate advisor. The friends who I have in the room just know, how wonderful of a relationship we've had over the years. The story I like to tell prospective students is that, through my career, as Jeff hinted, there were forks in the road. One of which was, should I follow Jeff up to Seattle? The next was, should I drop out of the PhD and go do this startup thing? In both cases, what really swung the decision for me was to continue working with Jeff. I think I've learned a lot. He's really shaped, not only my ability to do research, but the ability to sort of identify interesting research problems to tackle. As I reflect, there's one thing that gives me pause, which is when we first started working together, Jeff said that he considers students ready to graduate when they think that they're smarter than him. I'm not sure I'm there yet, but I hope we still end this defense well. So, the other person that I really want to thank, and really the person whose fault it is that I'm up here, is Jim Holland. He was my undergraduate advisor at UC San Diego. His HCI, Intro to HCI class is by far one of the best I've ever taken. And he has been sort of a source of perspective and inspiration and just advice throughout the years. And also Wendy Mackay and Michelle Baudouin-Lafont have just been two folks that I've always been, just had the greatest conversations with. They've encouraged me to think broadly. Some of my favorite memories of grad school have been in the back of their car as we've been driving around Paris, of which they've given me ample excuses to go visit, so I've never been unhappy about that. And of course, thank you to my committee for taking the time not only to be here, but also those slides that you just saw were, the result of a lot of advice that these folks gave me. Now, besides mentors, I've been really lucky to be a part of multiple institutions. Both, the Stanford HCI group back in the day, which looks very different, folks at, my startup, and also at the University of Washington. So it turns out we've not taken a lab photo in a couple of years, but really without these set of folks, I would not have been able to do sort of the research that I have done. And in particular, a shout out to Kanit Wangsapasawat and Dominic Moritz, who have been my collaborators on Vega and Vega Lite for a number of years, and really did a lot of heavy lifting that was needed. And besides sort of, collaborators who are friends, there are also friends who haven't been collaborators with, some photos that I've tastefully cropped to protect the innocent. But thank you, to all of these folks here for helping me stay sane throughout 6 years of graduate school. And last but not least, thank you to my family, my partner Meva, who's joining us via live stream. She has been, my teammate in every sense of the word. The fact that she and her family are staying up at, I don't even know, midnight Paris time, I think is a testament to that. She's just been there, counseling me through the low points, celebrating me through the successes, and having the patience of a saint as I get stuck on a Vega bug and I'm not always present. Finally, my parents, who have sort of unconditionally supported me, I'm really glad that they were able to be here in person today to see the defense. And so with that, happy to take questions. All of the work I've talked about is free and open source at that URL. We are about a week or two away from major releases of both Vega and Vega Lite. We're really excited to see where things go. Thank you. Yeah, Michael.
So I've been trying to think through this entire presentation. The core thesis at some level is the surprising ability to write sort of declarative specifications of interaction. And it's surprising in part because it has failed before. Like when you with say Microsoft's WPF and all these kinds of things, they really were trying to push toward a sort of declarative model, and weren't able to get far enough for this to really succeed in a meaningful way. Yeah. And I'm wondering
what's different? What's changed?
What about the sort of landscape here? Is it about something about about visualization being the strata that you're working on? Because you had this circle that connected to web design, and you think about
so the question is, folks have been thinking about declarative interaction for a while. how, what's changed about the landscape that this is now possible. So I think there are a couple things. First is that working in visualization has absolutely been probably sort of core to achieving this work. And that's because visualization is a much more sort of well-constrained, well-designed environment to tackle these questions, right? We know our input data. The set of primitives we're talking about were very well defined. And folks like Jock McKinley and others have looked at, how do we better formalize that, on the visual encoding side, that sort of, models. And so it was much easier to sort of build off that in that constrained environment than thinking about how do we do interaction design much more generally, but also declaratively.
So what are other domains or where it would or would not be possible?
Yes, so
multimodal interaction or like.
Yeah. So that's why I put web design up there, because now we're increasingly seeing sort of the similar approaches we've taken with Vega and Vega Lite in architectures like React and Redux and so on and so forth. So that's where the second part of, why is this work possible comes into play, and that's these reactive programming languages have become much more widely adopted, much more well-studied, and are generating these much more sort of domain-specific approaches to interaction. So Redux in particular, you can think of it as basically an architecture that is specific to the application you're working in right now. You're sort of message passing and manipulating interactive state, and it's all functional and so on and so forth. And we're already seeing, getting to that last point, some ability to reuse interaction techniques across Redux applications. So undo and redo, is the easiest one, and already, a Redux plugin exists for that. But now the question becomes, how can we better support people designing their sort of Redux languages? Can they prototype it, evaluate the expressivity of that language? Can we start to think of, are there notions of recursion in these languages and things like that?
Is there anything about, and then I will be silent, anything about the sort of architectural or abstraction insights that you've generated for visualization that you think would work in these more general, general is the wrong word, the web interaction context, like React and Redux? Like what can be sort of broadened and ported out, and what has to stay?
What can be ported out? I think the way I'm going to choose to answer that is by saying the concept of the Vega tool stack itself, I think, is the most powerful, one of the most powerful insights we've had. And by that I mean that, in the beginning there was just Vega. Or actually, technically it was like D3, but in the beginning, in the beginning there was Vega, and I mean, Jeff might have had an inclination that Vega Lite, that sort of Vega Lite existed, but I certainly didn't. And it was this notion that we're sort of building a whole variety of abstractions that sit one on top of another and play with each, are aware of each other, and you can fluidly move between. So I can take a Vega Lite specification, generate the Vega, and start just mucking around with the Vega, and possibly in the future go down to D3 and so on and so forth, right? And so it's this notion of having a very layered abstraction model that you can fluidly move between that I think is the sort of direction I would want to explore the other domains in. Yeah, Ben.
So awesome stuff, Arvind. One question I have is where you see the interface of machine learning and these more interactive tools like Lyra. So if maybe I have the data set isn't really fixed, I'm constantly transforming it and experimenting with different analysis of the data set itself. Do you think that Lyra would be used in generative visualization and then you plug different things as input, or kind of where do you see this interface?
One of the things I've been thinking about is, already on the sort of TensorFlow side of things, we're seeing similar sort of layered declarative abstractions for machine learning, right? We can go very high level, medium level, very low level, so on and so forth. But all of that is still happening through sort of textual specification. Is there room not only to use interactive visualization as an output of our machine learning models, so which a lot of folks are looking at. So how do we plug the output of models to a visualization, inspect it, analyze it, debug it, and so forth. But can we just use interactive visualizations from the start? Sure, maybe not for machine learning researchers or experts, But for the, the lay people who need to just rapidly generate a model for some part of their analysis process, can they start by just sort of maybe sketching out a neural net or something like that? We've already been seeing, some really interesting work coming out of Google Brain. Martin Wattenberg and Fernando Villegas' team in particular have been looking at, how can not only you use a visualization to sort of, sketch it out that way, but look at what each neuron is learning and things like that. And how does that change the process for, again, non-experts who want to use machine learning? Does that, make it more accessible and things like that? So that's where I see that going. Yeah,
This is a great talk.
thank you.
One thing I was thinking about is that you frame data viz as sort of, you have this data and now you want to visualize it.
Yeah.
So I was thinking with all the data that we now have on the internet, really accessible to everyone, can we have a framework where you start with a visualization and then you sort of automatically or something go get the data for it? So I start with what I want and then the system does the rest.
Yeah, that's a good question. So, can I basically do a reverse Google image search, but for a data viz, right? And folks, I think those systems in part already exist. So, some folks in the viz community have looked at, well, if I sketch out a time series trend, can I get a stock symbol that as closely as possible matches that trend, and so on and so forth. I think there's also been some work, I don't remember who has done it, that is much closer to the sort of reverse Google search of Google image search for visualization. So if I sketch out a bar chart, can I find an appropriate data set that would match that sort of trend that I'm visualizing or something like that? And one way in which I really want to study this is through the lens of computational journalism. So on these sort of new data-driven journalism sites, we're seeing users, not maybe all the users, but certainly a non-small subset, really deeply engaging with the data, commenting and so on and so forth. But right now they're just sort of constricted to these textual comments. What if instead we gave them tools that allowed them to, adapt the visualizations that the journalists had produced, maybe even link to other data sets, things like that, without having to figure out where are these data sets, how do I go get them, how do I clean them, so on and so forth, which also has overlaps to those sorts of questions.
That's really interesting. Just a point,
Yeah.
I didn't mean that this is a bar chart, I want data for it, but rather, here's a hashtag, I want to know the gender distribution of people who participate.
Oh, I
want
see.
sort of visualization. On this side it's the hashtag, on this side it's that. And that really is very close to what you're saying, where if I have that, then maybe people can build on it and say, oh, well, what about this hashtag?
Right. And certainly those systems, particularly plugging into the Twitter fire hose, a lot of those things already exist. But thinking about that sort of system design question much more broadly, yeah, definitely.
Any more questions?
Any more questions?
Okay, thank you.
Thank you. I draw your attention to the cookies and the fruit and the juice. We're leaving tomorrow, so please eat them. Otherwise, I don't know what I'll do with them. Maybe give them to 3B, but yeah. All right.
So this will end the public portion?
Yes, I'm going to end the live stream. See y'all later, folks. Thank you for joining. Wow, 13 people. All right.